Hi everyone! Alright, so we are back in Briggs section 3.3 today. So in the last couple of sections we've been introducing this concept of taking a derivative. Okay, and so today we'll kind of lay out some of the more formulaic rules. Okay, so this will be the key parts of how you would take most derivatives. Okay, it's important to know the limit definitions and stuff, but for the most part, moving forward, these will be what you use when you're calculating derivatives, and that's something like moving beyond this class. Okay, and so there's more than the ones we'll talk about today, but we'll kind of just talk about the first several today. All right, so our first theorem or rule is that if we've got some real number c, okay, so some constant c, if we take the derivative of that, it's always going to be 0. So and this will be anything, so if we're taking our derivative for this example, okay, we're taking the derivative of e to the pi. Okay, pi is just a number. E is just a number. E to the pi, still just a number. Okay? If it was e to the x, or if there was e to the pi plus x, if there was a variable thrown in there somewhere, x times e to the pi, then that would be a different rule. Okay? But, since it is just a number, okay, then this is just going to equal 0. Okay? Alright, so that was constant, and that's with anything. Okay, so f prime, I guess we could write this properly, f prime of x is equal to 0. Okay, our next rule, this theorem, is going to be the power rule. Okay, if we have some sort of non-negative integer, okay, so it's not a fraction, and it's not negative, then if we take our derivative, we bring the exponent down, and then subtract 1. Alright? So, in this case, if we took the derivative of this, okay, pi is our exponent. Okay, so what we're going to do is bring pi down front, subtract 1. So our derivative that we write out, so f prime of x is going to be equal to pi x times pi minus 1. Okay, and if this was a 2 or 3 or some number, we would just go ahead and subtract the 1 and write whatever the answer is. Okay, but because doing pi minus 1 would give us a crazy decimal, it's easier just to leave it as pi minus 1. Okay, so if it was something like let's do this, x cubed, okay, then f prime of x would be 3x squared, because we do the 3 minus 1 and then just write out the result of that. Okay, now notice something. Okay, how do I word this? You've got to actually have whatever the variable is that you're taking the derivative of. Okay, so just because there's an exponent doesn't mean you're going to use the power rule. So if we're looking at this function, so the function is given in terms of x. Okay, so it means it's named f of x. Okay, so it's got to be, to use the power rule, it's got to be whatever that variable is to a power. Okay, it could be a t, and then we would have to have t to some power, but it's got to be whatever that variable is to a power. Okay, if we look at this example I've got here, we've got m of x, and we've got a power here, so you might want to say, hey, power rule, but what do you have to check first? If we notice, what this is it's pi to some power. There's no x in here at all. Alright? There's no x in there at all, so that's going to say use the constant rule. Okay? So m prime of x is going to be equal to 0. Okay? So just because there's an exponent doesn't mean power rule. You've got to have that variable in there too, so there's a difference. Okay. Now, here we've got a proof, and you're not going to be asked to reproduce this. But I've got it in here just so you can see kind of where the power rule comes from. Okay, and so if you want more information on this, you can look at Briggs, page 153. Alright, but if we let f be some function that's a power function, okay, we can use our definition of our derivative with our limit. Okay, and then if we've got n equals to 1, and f of x equals to x, right, then we've got our derivative is equal to 1. If n is something greater than or equal to 2 with our power function, so x squared, x cubed, on and on. Okay, then our subtraction here is going to be x to the n minus a to the n, and the factoring formula is going to give us this. Okay, and so we can use our limit definition again and plug this in for our x to the n minus a to the n. These x minus a's cancel, and then we're able to just plug in a and evaluate the limit, and this is done n times. Okay, so it comes out to be our power rule formula. Now, remember I said you're not going to be asked to reproduce that, but there so you know just where it's coming from. Our next rule is going to be the constant multiple rule. Okay, so if we've got some function f and it's differentiable at some point x, and c is a constant, okay, can be a fraction, it's just some constant number, there's no variable. Then our derivative of that constant times our function is the same as if we pull the constant out and then take our derivative. Okay, so all this rule is saying is if you've got you're taking the derivative of a constant times some function, just pull the constant out, take your derivative, and then it's just your constant times whatever the derivative is. So if we look at this example, okay, we want to find the derivative, so we want to find ddx of our function. So the derivative with respect to x of our function here. So we've got our function of x. Okay, so our function of x is actually going to be this x to the 11th. There's our function. Our constant is this negative 7/8. So what we can do is use the constant multiple rule and pull out the negative 7/8. And so do negative 7/8 times derivative with respect to x of x to the 11th. Okay, now what rule is this going to be in here? So we evaluate the derivative the same way we have our derivatives before. So we see it's x to the 11th, so that says power rule. Okay, so that's going to be, we just carry the negative 7/8 along, and our derivative of this is going to be 11x to the 10th. So 11 minus 1 is 10. Okay, and then we can just multiply that 11 times the 78. We would get negative 70, oh, that's not a pen. Negative 77 over 8 x to the 10th. Okay. So if you've got a constant times some function, you can pull that out. Go ahead and take your derivative and then just simplify it. All right. Still using the same rules. Okay, and then we've got our next rule is the sum rule. I'm going to make a note and say sum or difference, because it works the same whether you're adding or subtracting. All right. Because remember, subtraction is really just addition with a negative. All right, but if we've got two functions, f and g, and they both have a derivative at whatever the point is, x. Okay, then we know the derivative with respect to x of the two functions added together is going to be equal to their derivatives added together. All right? So if I've got some long complicated function, for example, our polynomial here, what I'm going to do is take my derivative of each piece. Okay? So, and that's all the sum rule is saying, or difference rule. Okay? So for example, if we're doing p prime of x. Okay, so that's going to be the derivative with respect to x of 2x to 100 plus the derivative with respect to x of 4x to the e minus the derivative with respect to x of 17x plus the derivative with respect to x of 24 minus our derivative with respect to x of pi to the cosine e. Alright, so the sum or difference rule, okay, you're just going to break it down and take it chunk by chunk using those same derivative rules we've talked about before. So we'll do it piece by piece. Our first derivative is a power rule. So we'll bring that 100 down and we get 200 times x to the 99. Alright, no big deal. Then it'll be plus. Alright, with this one we'll bring down, it's still a power function, or power rule, so we'll bring down the e. So we have 4e x to the e minus 1. So just like pi, with e being that irrational number, it's easier to just leave it as e minus 1. Okay, and then minus 17 times x. So this one's going to be a did we mention that? I don't think we mentioned it, but so 17x, okay, if you've got a constant times a variable and the variable doesn't have an exponent, well, it does, but it's just a 1. So kind of a special case, okay, that derivative is just going to be whatever the constant is. So think about it this way. If I were to do that with the power rule, we'll do a little side note over here. So the derivative with respect to x of 17x. Okay, so let's say we know this is the next to the 1. So let's say we do the power rule. Okay, so the 1 comes down. So we have 17 times 1 times x to the 1 minus 1. So it's 17 x to the 0. X to the 0 is just 1, so this is just 17. Okay? So anytime your variable, okay, just has an exponent of 1, okay, then that your derivative is just going to be whatever that constant is that you had to begin with. All right, and so then I'll take the derivative of this 24. So constant multiplier rule is just a constant, so that'll be plus 0. And then my derivative of pi to the cosine e. Pi to the cosine e is just a constant, so again, that'll be a minus 0. Which we leave as is. So our final answer would be 200 x to the 99 plus 4 times e times x to the e minus 1 minus 17. Okay, so sum and difference rule, we'll just take it piece by piece and take your derivatives with your derivative rules that we've already talked about. Okay. All right, our second to last derivative rule for today. We're all this section. So remember we defined the number e several sections ago using our limit. Okay, so the number e is just that irrational number that satisfies this limit. Okay. Remember that it's the base of the natural exponential function. So e to the x. All right. You can also look at using the infinite limit. So our derivative of e to the x. So remember, e is just a number. So the derivative of e would be 0. But e to the x is a function. Okay? So if e to the x is a function, and it's differentiable for all real numbers x, and in fact, the derivative is itself. Okay? So you can think about it, if we were to take our e to the x and take the derivative of it, we can use our limit definition from up here. And what's going to happen, if we do some algebra, we get it down to just e to the x. Okay? And again, that's not something you're going to be asked to reproduce, but just so you know, it's where it comes from. But the main thing to remember, okay, derivative of just e is 0. Derivative of e to the x is e to the x. Okay, and granted, it still has to obey all the other rules. Okay, so for example, if we want to find the derivative of our function right here, we've got the e to the x in here, alright, but it still obeys all the other rules. So what it is not is this is not the same thing. Okay? Not the case at all. Alright? What it is instead is, so we'll take the derivative of, what is it, 7e to the x minus 14x to the e. Okay, so if we're taking the derivative of this function, we see, okay, well, it's the sum difference. So we'll split it, and we'll do the derivative with respect to x of 7e to the x minus the derivative with respect to x of 14x to the e. Okay. All right, so then this first piece is constant multiplier rule, so we'll bring the 7 out front. So 7 times the derivative of e to the x. And the second one, we'll bring the 14 out in front, so 14 times the derivative of x to the e. All right, so derivative of e to the x is just what? E to the x. Okay? And derivative of x to the e, we use the power rule. So that is e times x to the e minus 1. Okay, and that would be our final answer. Okay, because we can't combine those in any way, really. Okay. Alright, so there's e. The last thing we'll talk about for this section is higher order derivatives. So we've just been doing the first derivative. So we've taken the derivative one time. It's possible to do this multiple times. So we'll have the second derivative or the third derivative. So the second derivative is, guess what? The second derivative is just the derivative of the derivative. Okay? Alright, so it's just the derivative of the derivative. That gives us the second derivative. We've taken the derivative 2 times, second 2. Alright, we can also go past this, and we can go to the nth derivative, as long as n's greater than 1. So we can have like the 42nd derivative, the 112th derivative. Alright, so the nth derivative is defined like this, and really all it is you taking the derivative of however many times until you reach n. Okay? So it's the derivative of the derivative of the derivative of the derivative until you reach n. Okay? So, for example, if we want to find the first, second, and third derivatives. Okay, so the first derivative is what we've been doing with our rules. We'll take the derivative the first time. So we'll take our function here, and first what we'll do is write it, okay, so it becomes, oopsies, sorry about that. Sometimes clicks can go off sometimes. Alright, so what we'll first do is, because we don't know how to take the derivative of this, right? We don't know how to do that. But I can distribute this, and we get two times x squared plus x squared times x to the negative 1. Okay, and this piece simplifies to be x to the 1 because you add your exponents. Okay, so you have f of x is equal to 2x squared plus x to the 1. Alright, so we'll take the first derivative of that. Okay, so we'll do, it is 4x, because we bring the 2 down, and then 2 times 2 is 4, and then 2 minus 1, or 2 minus 1 is just 1. Alright, so we have that, plus, so the derivative of x is going to be what? Well, I've got a 1, it's just x to the 1. If I bring the 1 down, I get a 1. 1 minus 1 is 0. So, my derivative of x is just 1. So there's my first derivative. Now I can take my second derivative. So I'll take the derivative of my derivative. Alright, so we'll do it again piece by piece because it's some difference still. So we have the derivative of 4x, which is just going to be 4, plus the derivative of 1, which is just constant, so that'll be 0. Okay, so that's just 4. And then our third derivative will be the derivative of our second derivative. So our derivative of 4 is 0 because it's a constant. Okay, so you can kind of see if we look at it, we start out with this polynomial, and as we take the derivative, especially as these terms move to be constants, we end up with 0 eventually. Okay. Another way you might see this would be if we wanted to find all the derivatives of a function. So, for example, if I had this one and it wanted me to find all the derivatives of some function. Okay, most of the time, if you keep taking these derivatives of the derivatives, eventually it'll taper off to be 0, like our example did up here. Okay. So we can find, first we'll find the first derivative. So y prime is just equal to 1 over 120 times x, times 5x to the 4th, which is just 5 over 120, which is which is just 1 over 24. I thought it might be easier if we simplify the fractions a little bit. All right, so there's your first derivative, okay? So we can go ahead and take our second derivative. All right, so the first derivative we can mark with a prime. Second derivative we can mark with a double prime. All right, so we can do, it'll become 4, or we'll write it out like this, 1/24 times 4x to the 3rd and so that simplifies to be 1/6 x to the 3rd. All right, so first derivative we can mark with a prime. Second derivative we can mark with a double prime. And third derivative, I made a typo here. Third derivative we can mark with either 3 primes, or what's common is to do a, whatever it is, y, with a little parentheses around your exponent, and the number being whatever derivative it is. Just because, I mean, after a point, like, you can't have the 5th derivative and have like, it's too cumbersome to write it with the primes. Okay, so eventually you can switch and do, okay, the little parentheses with your number, and that number is whatever nth derivative you're on. So for the third derivative, we can write like this. Okay, and that's going to be 1/6 times 3x to the x squared. Okay, and that becomes 1/2 x squared. All right, and then we can do y to the 4th is equal to 1/2 to the x. So just x. Y to the 5th is just 1, because the derivative of just x is going to be 1. And y to the 6th is going to be 0, because we're taking the derivative of this constant. Okay, now, once my derivative goes to 0, any higher derivatives I'm going to take of this are just going to keep spitting out 0. Okay, your derivative of 0 is always just going to be 0. Alright, so if I could keep going, and y to the 7th still be 0. Okay, y to the 100th still be 0. So what we do is we'll write it as y to the we'll say k is equal to 0 for k greater than or equal to 6. Okay, because 6 is when was our first derivative to go to 0. Alright, so we found all of our derivatives of our function. Okay, and if they ask you to do that, that's what they're looking for, is just keep evaluating the derivative until it goes to 0, and then make a note somehow, like that, saying that everything beyond this is going to go to 0. Okay. Alright, I think that is it for section 3.3. Okay, I'll upload some other examples for you to practice with, so you can get practice just finding the derivative. Okay, and then don't forget you'll have a learning activity as well on finding derivatives. Alright, I will talk to you either in office hours or during our next video.